Monday, Monday? Oh, Jesus Christ, Easter holidays messed me up. So on Friday we did question 1, 2 and 3, and like I said, we went through all the extra tips, hints, etc, etc. So I'm not going to go through that now, that's all on YouTube, and you can access it there. However, what we're going to start on is this question here, question 4, and that's about radioactivity. They got the same number of marks, yeah? But like I said, I'm going to go through some extra bits, so hopefully it should be relatively, it should cover a larger range than what they've said in the actual papers. But isotopes, when we talk about isotopes, so this is part of chemistry and it's part of physics. Isotopes are things, if you notice, isotopes have the same number of protons, but they have different numbers of neutrons. So they have different numbers of neutrons. Now the key thing that you need to understand is, another way to say it is, they have the same atomic number, because atomic number is just the number of protons, but they have different mass numbers. Now, if something is an isotope, typically, if you think about carbon 12 is pretty stable. Carbon 13 and carbon 14 aren't very stable. So what happens in nature, everything will try and get to a point of stability. So these will try and get to a point of stability. Now, how do they do this when it comes to the nucleus? Ultimately, you have to have some form of radioactive decay. Radioactive decay. Now, with radioactive decay, one of the important things to understand is that in order for radioactive decay to happen, there are, as far as you're concerned, there are 4 mechanisms, okay? So if I did the number of protons versus the number of neutrons, so the number of neutrons versus the number of protons, if I did a 1-to-1 line, it would look like that. But the line of stability looks kind of like this. So anything that's up here, those atoms are too big, because everything's trying to get down to iron and nickel, which is the most stable thing. So what happens up here is you have alpha decay. Now alpha decay, I'll talk about that in a second. And if you've got too many neutrons, which is this bit up here above the line, so this bit up here, what you're going to have is beta minus decay, and underneath that line you're going to have beta plus decay. One of the things that you need to know for your exam is how beta minus decay works. We'll talk about that, like I said, in just a second. But there are 3, like I said, types of radiation that you can have. What are the 3 types of radiation? Someone tell me in the chat. What are the 3 types of radiation? Someone tell me in the chat. Someone tell me in the chat quickly, come on. Gamma, beta, alpha. Well done, Callum. Well done, Mia. Right, so the 3 types, good, well done. So the 3 types of radiation you can have are alpha, beta, and gamma. Now, you need to know these 3 types of radiation, and you need to know their properties. So when we talk about alpha, it's got a mass number of, alpha has a mass of 4, and it's got a charge of +2. So an alpha is going to be very much like a large bowling ball when it's moving through. When it's moving through objects, it will be very much like a large bowling ball. It has a very high mass, and it's got a strong charge, so therefore it's gonna, whenever it goes past something, it will ionize it very, very quickly. However, it will lose that energy very quickly as well, because it's got a very large mass, so it doesn't travel very far. Beta particles are electrons, so they have a mass of 1/2000 atomic units, but so they are very, very small, but they've got a charge of -1. And when we talk about gamma radiation, so this beta particles are more like ping pong balls, right? So if you throw one, it's very likely going to bounce all over the place. However, if you talk about gamma radiation is just pure energy. It's part of the EM spectrum, and excess energy is emitted using or via the mechanism of gamma radiation. Excess energy, and that is just an EM, electromagnetic wave. Okay, so that's all well and good. How does beta decay actually help reduce the numbers? What happens in beta decay is you end up with one of the neutrons So let's do this one here. Let's do carbon 13. One of the neutrons will decay. How does beta decay work? Sorry. One of the neutrons breaks down into a proton and an electron. My OneNote's messing up, one sec. So, here we were. One of the neutrons breaks down into an electron and a proton, and this thing is emitted. This one is shot out from the nucleus. That's why we get beta decay in the first place. Last thing I'm going to talk about is what do these need to be stopped by. So alpha can be stopped by paper. Beta can be stopped by a thin layer or a few millimeters of aluminium sheet. And then finally, you've got gamma radiation, which has to be stopped by thick lead. Okay? Right, boys and girls. If what I'm going to do is I'm going to zoom out before I look back at the question and give you a chance to take a screenshot. Give you a chance to take a screenshot of everything that is on the screen. Hopefully you can see all of that. Let me know if I need to move it. Tell me if you're okay with it. Tell me in the chat. If you've not shared it, make sure you share the live, please. Make sure you share the live, please. Right, okay. Ready to go? Boys and girls. So, let's go back to the question then really quickly. What is an isotope? Someone tell me in the chat really quickly. Someone tell me in the chat, what is an isotope? The collective power of everyone. What is an isotope? Oh, we're up to 30. We got some traction. Let's go. So, good. Well done, Ellie. It's the same number of protons, but different number of neutrons. Okay, so it's the exact same definition as in chemistry. It's the same number of protons, but it's different numbers of neutrons. Now, carbon-14 emits beta radiation. Describe the structure of a beta particle. The beta particle is going to be really straightforward in terms of describing it. It is got 2 marks, but all very simply, I need you to tell me 2 things. What is happening here? Oh, that's why it keeps messing up. Sorry, my keyboard was doing bits. Right, let's try now. Beta particles What can you tell me about the structure of a beta particle? It has got a charge of -1 and it has a mass of 1/2000 of a proton. Okay, so good, well done Peachy. You've got a charge and you need to describe the mass when it comes to the structure of a beta particle. That's literally all they are asking. Let me just check on the mark scheme really quickly. Yeah, and ultimately it is a fast moving electron. That is the 3rd mark. Good, well done. Right, a person wants to confirm that the source is giving off beta decay. Remind me in the chat, how do I stop beta decay? Good, well done Isabella, well done Rayan. It's going to be a few millimeters of aluminium. Okay, now last one on this page is this decay equation. So I talked about, yes Johnny, this is AQA higher. Good, well done Peachy. Thank you Chris Tuition, I appreciate you. During beta decay, carbon-14 nucleus decays into a nitrogen-14. Complete the nuclear equation for this decay. So what did I say happens to the mass number? The mass number is going to stay exactly the same. And good, well done, Rayan. So the answer is going to be 0 for the top one, and it's going to be -1 for the second. Now notice the numbers at the top, the mass numbers, add up to 14. And the atomic numbers add up to 6, because 7 plus -1 is going to equal 6. Okay, T, so we know, let me go back to this then real quick, T, let me explain this. So if I look at an alpha particle is just helium. So another way to write an alpha particle is just do the alpha symbol. It's got a mass number of 4 and it's got 2 protons, so we say 4 and 2. Yeah, beta is going to have 0 and -1. So therefore, when I look at it, when I do a decay equation, just like anything else, just like a maths equation, all the numbers on both sides of the arrow have to add up. So 14 is going to be 14 plus 0 because it's a beta particle, and then -1 for the atomic number. So I appreciate that some people might find this particularly difficult. So what I want you to do is in the chat, if you can tell me what is A, what is B, what is C, what is D, what is E, and then answer question 3 for me. Johnny, come on. A is -1. Well done, Isabella. So we got the first one. A is -1. How do I know it's -1? Because the numbers for a beta particle and an alpha particle are always going to be the same. Okay? The numbers for an alpha particle and a beta particle are always going to be the same. Now, what is B? What is C? B is 99. I've got a few people that are telling me B is 99 because, wait for it, what particle is it? What particle is it? Remember, I'm going to put it on the side here. If you did not remember, an alpha particle has a mass of 4 and atomic number of 2. Beta has a 2. Beta has a... Are we back? Boys and girls, it just glitched on me. Tell me in the chat. Someone type in, I don't know, lemons or something, so I know we're back. Cool, thank you very much. Right, boys and girls, so you can see that the alpha particle is always going to be the same. Now, if that's the case, what's B going to be? Now that I know that piece of information, what's B going to be? Thank you, Mankind. Thank you, Isabella. Thank you, Sabiha. 95. Good, well done, Mankind. It's going to be 95 because the two numbers added together at the top have to equal 99. Okay, and then the bottom number, what's the bottom number going to be? 38. Good, well done. Right, very quickly, tell me in the chat if you want me to do one more like that. Do you want me to do one more question like that? In fact, have a go at question 3. What is the atomic number and the mass number? What is the mass? No worries, I will. And what's the atomic for question 3? What's the mass and what's the atomic number? So I've got G, 151 and 72 decays by alpha decay. Remember, the numbers for the alpha decay are always the same. So what is the new mass number for element H? Someone tell me in the chat. What is the mass? Is 147, Isabella. Well done. Good, well done, Callum. It's 147, and in the bottom one I've just got to take away 2, so the answer is going to be 70. Alright, we're going to do one more really quickly because everyone in the chat seems to say one more. Right, I've got let's say Amir is the last one that commented. So Amir, I'm going to say my mass number is, I'm just literally looking around for numbers now. Let's go for 124 and let's go for 52. This decays by alpha decay. So what's the new numbers going to be? So A goes into B, Good, Isabella. Well done. I think we're a lot better on this now. So it's going to be 120, 4 and 2, 120 and 50. Because I've got to take away the 4 from the top number and got to take away 2 from the bottom number. Well done. Now I'm going to do one more, and this one's going to be a beta decay. So let's say C breaks down. So we got carbon, I don't know, 14 and 6. This decays by beta decay. So what numbers have I got? Just listen to the question. What numbers have I got for beta decay for my atomic and my mass? For beta decay only. I've not even told you about anything else yet. Start with that. For beta decay, what are the two numbers that I'm going to write? So this one and this one, what are the two numbers? 0 and -1. Well done, Hanfei. So that means that the top number is going to be 14 and the bottom number is going to be 7, like most people said in the chat. Well done. So this would be a beta decay example and this would be an alpha decay example. I'm going to leave them on the screen. If you want to take a screenshot quickly for me. Take a screenshot quickly for me. So these are the two examples of the alpha and beta decay. Gamma, nothing. So Amir, that's a very, very good question. So Amir asked what happens in gamma. In gamma, it's just going to be energy is released. So you've got carbon 12. Say you've got this. When it breaks down, it's going to have some excess energy. So because it's got excess energy, it's just going to remain the same. And it's going to emit a gamma radiation. Don't talk about particles yet. Because T, what's 6 plus -1? Because it's a negative atomic number, because it's not actually an atomic number, it's the charge of the particle. Because it's the charge of the particle, 6 plus -1 is actually going to give you 7. Yeah? Does that make sense? Tell me in the chat, T and N. Good, thank you. Right, so because the beta particle has got a, no worries, because a beta particle's got a -1 there, you have to kind of, instead of taking it away, you add the number. Right, and this is gamma radiation. So I'm going to leave it on the screen. In fact, I've left it on the screen for long enough. Hopefully you've had a chance to take a screenshot. If you haven't, make sure you do, or tell me in the chat, otherwise I'm going to move on. So that's the decay equation. Okay, now the next bit is you might be asked in the exam to plot a graph of activity versus time. So if you look at the numbers, that's the example of the question. I've plotted a few of them already just because I wanted to try and make sure this was as smooth as possible. So the last three I need to plot are these three. 6 and 50, I'm just going to put across there. 8 and 25, so I'm going to put across there. And then this one, 10 and 12.5, is going to be, I swear, this is bugging me. I don't know what's going on. I don't know if something's being pressed. My pen keeps crashing. There you go. Okay. Right, anyways. Point being, we've got, now what we need to do is we need to draw a line. So that line is going to be a smooth curve going through all the points. And it looks like this, and the last point is going to be over there. Okay, so Kush, this is AQA, this is AQA. Edexcel is going to be next Thursday. Right, so that's my points plotted, and that's what my graph looks like. Now use the graph to calculate the half-life of the isotope. Half-life, in terms of the definition, there are two definitions that you can give. Half-life is the amount of time it takes for, and two definitions you can give, choose whichever one you feel better with or feel more comfortable with, the initial activity to half, or the other one you can give is the number of radioactive particles to half. Okay, now this question, it says, if I zoom in, this question says, show clearly on the graph how you obtain the answer. So in order to show clearly on the graph, I have to do a little bit of, what do you call it? I have to do a bit of showboating for the examiner. So I have to say, right, this is 400. So I have to circle 200 or show that I've halved it. And then I go across to the line. And then I go down from the line. And then I get 2 seconds. And then I do the same thing for half of that again, and I get 2 seconds again. So I get 2 seconds, and then I get another 2 seconds. So LM is going to come down to revision and 3 and 4 mark questions. Okay. So the half-life is 2 seconds. And you will get both marks if you've drawn the lines on the graph. You will get both marks. It's automatically assumed that you use the graph. Okay, so please don't panic if it seems like there's not a lot of work for not 2 hours. I messed up. Not 2 seconds. It's going to be 2 hours. Yeah, right. Are we happy with radioactivity? Is there anything anyone wants me to go over? Right, boys and girls, we've got about 38 people on the live at the moment. We need to try and get it up to 50 before I go through question 5. If there is anything that you want to ask me, put it in the chat, please. If not, very quickly, share the live for me. Let's get to 100 people tonight. I'm excited. I want to try and get to 100 people if we can make it before we get to the end of the paper. Share this live with at least one person. Okay? So, if you look at how long it takes, so Isabella, what you do is you go to the left hand, or you go to the y-axis, where the point meets the line, that point there, or where the graph starts, you half that number, and then you draw a line across, and then down, and then you get whatever the number reading is, that's going to be your half-life. You can also do the same again, so half 200, I get 100. I go across, draw a line across to the line, up to the line, and then down, and then look at the difference between these two, and that's going to be 2 again. Yeah? Yeah. T, you get marks for that. So that's why it's worth 2 marks, because you have shown the examiner that you've used the graph for your answer. Yeah? Cool. Isabella, that's probably the best. I know you haven't made a noise, but the fact that you typed it, that's one of the most rewarding sounds a student can make. Will, I can, but I won't do it today unless it comes up in the exam. In fact, it is coming up. It's literally, this question is on mains electricity, Will. So it's like I planted it. Right, boys and girls. So I'm assuming you shared a live, by the way. When you talk about circuits, there are 2 types of current. So when we talk about electrical circuits, there is direct current, okay, and I've pre-written the definitions just to speed things up. There is direct current, where current flows in one direction only, okay, and then there is alternating current. Now alternating current is the same that you get from your mains electricity. Alternating current, these electrons move a very short distance. They move back and forth. So the current repeatedly changes direction back and forth. Now, because of that, it has a frequency. With direct current, whenever you talk about batteries or cells, we are referring to, or they will produce, a direct current. When you are talking about mains electricity, anything that is plugged into mains is using alternating current. The reason why laptop chargers have such a big bulky thing on the end of them is because they take alternating current and then they convert it to direct current so your laptop battery can charge. Okay, that's part of the reason why it works. Now, when we come to mains voltage in the UK, you need to know 230 volts, and you need to know a frequency of 50 hertz. 50 hertz is 50 times a second, so that means these electrons are going to switch direction, go back and go forth 50 times per second. Okay? 50 times per second. Now, that's kind of the background to the question. Let's actually have a look at the question now and let's see what it's asking. Describe what is meant by alternating current and explain how it differs from batteries. That is the definition, or rather that is literally this answer here, these notes here. You just need to say what they are. So I'm going to now put it into slightly more exam specific words. Alternating current is a type of current where the flow of electrons reverses direction periodically. And then the next bit is how does it differ from direct current. So whereas direct current flows in one direction only. Okay, right. Yes, Ellie, the definitions I wrote first, if you just wrote them in the correct order, you absolutely get the marks as well. Right, in this, changes in direct from positive to negative potential difference. Changes in alternating from positive to negative potential difference. I think that's what you're trying to say. Changes in alternating from positive to negative potential difference. So the potential difference constantly switches back and forth, yeah? What is the potential difference of the UK mains electricity? Let's see who was listening. Someone tell me in the chat. What is the PD? What is the voltage for mains electricity in the UK? Someone tell me in the chat quickly. 230. Well done, Callum. Well done, Raikindis. 230 volts. Who was listening? What is the frequency of mains electricity in the UK? Tell me in the chat quickly. What is the frequency? Good. Well done, Isabella. Well done, VMH. Well done, Callum. Well done, Dawid. Well done, T. So, next question. A laptop has a power rating of 115 watts. Calculate the current flowing through the laptop when it's connected to the main supply. So I've got three things. I've got the power and I've got the voltage, and I need to work out what the current is. So very simply, I'm just going to have to rearrange that equation. That's going to be P divided by V, and I put my numbers in, so 115 divided by 230, and I get an answer of 0.5 amps. Okay, I get an answer of 0.5 amps. Now, next one, the next question is calculate how much charge flows through the laptop when it is used for 2 hours. Again, I've written the equation in just to make life a little bit easier. Do I know my time? Yes, it's going to be 2 hours. And then do I know my current? Well, my current is just going to be the same as the previous question, so 0.5 amps. So I just have to do Q is equal to 0.5 multiplied by 2, which is equal to 1 coulomb. Is that correct? Is that correct, boys and girls? Have I done the right thing? I've looked at the current and I've looked at the time and I've just multiplied them together. Have I done the right thing? Someone tell me in the chat. Have I, Callum? Think about it. Do I need to do it in minutes? There's a couple of people that are asking. Time, make sure you write this down, please. Time is always in seconds. Seconds. You have to convert 2 seconds. Okay, good, well done, Ellie. So that's one of the key mistakes that a lot of people make when they do this question. All right, you do. So I'm going to rub out all the rest of this. because I need to convert 2 hours into seconds. How do I do that? Well, I know it's going to be 2 multiplied by 60 minutes in an hour multiplied by 60 again for seconds. Good, well done, Star. So I now get 0.5 multiplied by 7,200 seconds, and that's going to give me an answer of 3,600 coulombs. Please, please, please don't make this mistake. It is a very, very simple mark to get in the exam. Time is always in seconds in physics, okay? Alright? So, boys and girls, I think that's the last part. Sorry, I'm just dying. Oh my god, I don't know what's happened. Right, okay. Guys, what we're going to do is, no, I'm joking. I'm fine. So, it's all good. It's all good. Right, boys and girls, what we're going to do is we're going to do question 6, okay? But we've done question 5. We've done question 4. It's only 6 and 7 left, so we're about halfway through the session. We are bang on time. However, very quickly, I'm going to take a very quick break, like literally a minute. Don't log off, but do share this live with someone right now, okay? Please make sure you share this live with someone very, very quickly. Right, okay. Sorry, just had to check something. Right, so, very quickly, if I look at this question then, this question is about specific heat capacity. Now, this is one thing that a lot of students really, really either hate or they've worked out how to do it, and therefore they are pretty straightforward and they enjoy this type of question. This question is really straightforward if you know what you're doing, okay? So, boys and girls, a student investigated how the temperature of the oil increased when heated. Student used electric heater to heat 2 kilograms of oil in a container. Remember that, 2 kilograms of oil. Diagram below shows the equipment, how the equipment was set up. So you get 4 marks in this question, and you have to give 2 ways in which the student could improve their setup. So in order to, I don't know what it is that seems to be slowing down my computer. I'm just going to check something. I don't know if it's this or if it's something else. Right, okay. So, you get 1 mark for saying the explanation, and you get 1 mark for one method, and then 1 for the explanation. So I'm going to put them in fact, I'm going to draw them on the screen. What's the first thing I could do? Use a lid and insulate cup. Good, Callum. Someone's been doing practice questions. So, absolutely, you're absolutely spot on. Number 1 is use insulation. And that is how you could reduce the amount of energy lost to the surroundings, and that's the explanation for it. The second thing you could do the second thing you could do is thermometer. Next thing I could do is put the number 3, I could put the thermometer in the middle. And number 4, what I could do is I could stir. Okay, so those are the different ways that you could take this experiment and you could improve it and make it more accurate. So I'm gonna just copy him, as in this is from the mark scheme, but this is exactly what the mark scheme is saying. So if I say number 1, the student could insulate the surroundings. Student could insulate the container and reduce the heat loss to the surroundings. Number 2, student could use a thermometer with a higher temperature precision. Number 3, student could use a more accurate power source. We didn't talk about that. A power source which is regulated, or the student could stir to ensure that there's uniform heating across the board. So that is the, no you don't, Thomas, so you have to write 2 of these. So you have to write 2 of these. So you can choose insulation and digital thermometer, and that would be absolutely fine for all 4 marks. Yeah. So it's the method, how you're going to improve it, and then the explanation. I've just put all 4 just for your own understanding, okay? I'm going to zoom in. I'm going to let you take a screenshot. If you have not taken a screenshot, I'm going to keep it there. So, like I said, please don't panic. You don't have to write all of that. You just have to write 2 out of the 4. That's fine. That's all good. Thank you for asking, though. Right. 2B, I have been going through triple science. We've done the first half of physics already. I'm going to do the second half of the physics paper, which I made next week Thursday. So if you want to join next week Thursday 8 p.m, this is where I'll be, okay? Right, question 6.2. The specific heat capacity of oil is 2,000 joules per kilogram degree Celsius. The temperature of the water increased from 25 to 75 degrees. Let's see who was paying attention then. Q is equal to the mass of the object. We will come back to that. C, which is 2,000, and then the delta just represents the change in. So what's the change from 25 to 75? Someone tell me in the chat quickly. Someone tell me in the chat, what's the change? Good, well done, Callum. So it's going to be 50 degrees Celsius. Now, who remembers what the mass was? Who remembers what the mass was? Because I'm doing this question. I'm in the exam. Good, well done, Hanfei. Well done, Callum. I did draw your attention to it, but the point I'm trying to make is sometimes in the question, they won't give you all the information in the same bit. What you actually have to do is you have to go back to the beginning of the question, because they gave you a small piece of information at the top. So don't forget that piece of information. If the equation doesn't seem to add up, if there's something missing, just scroll back up, okay? So it's going to be 2 times 2,000 times 50. Someone put that in the calculator for me. What do I get if I do 2 times 2,000 times 50? What do I get if I do 2 times 2,000 times 50? 200,000. Well done, Hanfei. 200,000. And then what are the units for this? What are the units for this? Because I haven't given me the units. What are the units for this? I've just worked out energy. Thermal energy. Good. Well done, Hyperdominion. Oh no, I don't even know what your name says. Hyperdemoine. Cool. Well done, Ellie. Well done, Isabella. Right. Okay. So, next one. The heater was switched on for 10 minutes. Again, we're back to our same thing. Energy is going to be equal to, so energy is going to be from the previous question, which is 200,000. 200,000. And what do I divide by? Because I know now that I definitely don't divide by 10. What do I divide by? What do I divide by? 600. Well done, Ayushan. Well done, Raikindis. It's going to be 600 because I have to take this 10 minutes and I have to convert it to seconds. So I'm going to have 200,000 divided by 600, and I should get an answer of 333. What are the units for power? What are the units for power? Someone tell me in the chat quickly, what are the units for power? Yeah, Theo, what are the units? No, Raikindis, what are the units for power? What? Jana, Ellie? Sorry. I couldn't help it. I'm sorry. Right, I'll stop. Right, what are the units for power? Right, boys and girls. And then the final one, what is meant by internal energy, okay? So, internal energy. Now, this is the kind of basic definition of internal energy. Good, well done, Callum. On it straight away. So, internal energy is the sum of the potential energy plus the kinetic energy of all the particles in a substance. I've broken this down into 2 marks. This is where the 2 marks come from. Internal energy is the sum of the potential energy plus the kinetic energy, and then the second mark is for saying of all the particles in a substance. Now, sometimes in some definitions they will refer to this as the thermal energy of a substance, and potential is actually chemical potential energy. Chemical potential energy. So when we talk about this is all the sum of all the chemical and the potential energy. Kinetic is thermal, yeah. Theo, in this particular example, because we're talking about the kinetic energy of the particles, we are talking about thermal energy, okay? So, what does that mean? Well, actually, if I zoom in here, I know it's not the best image, but I tried to find something that helps you to explain this. If I've just got a gas, it's just going to have kinetic energy, whereas if I've got molecules, they're going to have kinetic energy, and they're also going to have vibrational and rotational energy. You don't need to worry about what that is. But when we have liquids or solids, we also have to consider the potential energy of the bonds between them. Okay? Chemical potential. Right, so I'm happy to explain it. As in, this is the way I think of it, sir. Please, by all means, jump in. I'm always happy to learn and try and make it do it better. When we talk about potential energy, chemical potential energy, there's two types of chemical potential energy. There is the chemical potential energy that is stored in bonds. But what you also have to consider is the chemical potential energy that is not just stored in the bonds, in the covalent bonds between molecules, within molecules, but you also have to consider the intermolecular bonds that form between molecules. So these are the intermolecular bonds. And in these intermolecular bonds, what you've got to do, if you think of something changing state, what you've got to consider is when you've got an object changing state. Here, when I'm increasing the temperature of something, right, this is part of the energy topic, but it's the last part of the energy topic. So when you talk about increasing the temperature, what you're doing is you're increasing the kinetic energy of the molecules. Whereas when you are talking about the phase of melting and freezing, what you are doing is increasing or breaking intermolecular bonds. So that bit, that's kind of what you need to understand when we talk about the chemical potential energy. When you are breaking... No, Angel, this is actually physics. So the breaking of intermolecular bonds is the bit where you melt and you freeze. Hence why the temperature does not increase when you are melting and freezing or when you're vaporizing and condensing, because temperature is directly proportional to the kinetic energy of the molecules. You don't have to know that as in why until you get to like A-level physics, but temperature is directly proportional to kinetic energy. So when we talk about this, the thermal energy, that is basically talking about the kinetic energy or the temperature of the part of the molecules. So let's break that down then. Let's have a look at this. Internal energy is the total kinetic energy and potential energy of all the molecules / atoms in the substance. Okay? Right. Now, last one, and this is kind of why I was talking about this. State one factor, in fact, no, not that bit, the last bit, which I'm going to talk about in a second. So, state one factor that causes the pressure of gas in a sealed container to increase when it is heated. What factor could it be? Good, well done, Callum. It's going to be temperature. Temperature increase causing particles to collide. You don't need to write all of this. You could get away with temperature. With the walls faster and more often. Two things, they collide faster and they collide more often. People always forget the more often bit. Last one then. Student heats a substance as it melts. Define the term specific latent heat of fusion. Now I'm going to do two things. I'm just going to put the definition or the answer on because it's a bit bulky. So I'm just going to put the answer on for the time being. Specific latent heat of fusion is the amount of energy required to change the state of 1 kilogram of substance without changing its temperature. That's really important. So this is why I had the graph here in the first place. Notice that when something changes state, it does not change temperature. If you are doing chemistry, then the reason for doing this, or rather one of the ways that you know something is a pure substance, is it has a fixed melting and boiling point, whereas if it was an impure substance, it would the line would look like that. It wouldn't be a flat line, it would increase slightly. No, Isabella, that's specific heat capacity. So there's two different things. In fact, let me just do it here. So there's specific heat capacity. Now if you look at the definition of specific heat capacity from the equation, it's Q divided by M delta T is the amount of energy needed to increase the temperature of 1 kilogram of substance by 1 degree Celsius. Notice temperature 1 degree Celsius, mass 1 kilogram of substance, Q energy needed. Whereas when we talk about specific latent heat, L, is the amount of energy needed to change the state of 1 mass of, so let me write it, energy needed to completely change the state of 1 kilogram of material without changing temperature. They are very, very similar, Isabella. You're absolutely right. So Q, energy needed, M, 1 kilogram of material. So in this one you don't have temperature. User 853-476-222-6101. Yes, I can. Yes, I will after this live is finished. That's absolutely fine. Right, okay, I really want to get back to the question, but hopefully that makes sense. T, this could come up on a foundation paper. You are expected to know both of them. Oh, that is the end of that question. Right, last question and really quickly. Are we ready for this? Last question, we got about 10 minutes, okay? Because I have rearranged the equation for the words, motives. Because what I've done is I've just rearranged the equation to make C the subject and L the subject, so that I can define what it means. I can use the equation to define what it means. Yeah? I've just rearranged them. What is the state, what happens part? Ellie, I'm not sure what you mean. Say that again. Just ask me again. I'm guessing you mean this bit. I'll leave that on the screen for a few seconds because, like I said, I know it is slightly more complicated. So I wanted to give you a time to take a screenshot. By all means, go away, write this down, look this up, Google it, make sure you understand it before the actual exam, okay? Very, very short. AQA E- or E. Second part of the question. Right. I don't know what happened there. Right. During melting, the internal energy of the substance increases. Is that the bit that you meant? Okay, cool. Right, I think we're good. Right, boys and girls. So, last question, and really quickly, we're up to, we're down to 33 people. Come on, guys. Who's not sharing it? Who's jumping off? Who's getting tired? It's almost there. 9 minutes. Let's go. So, these are the energy stores and these are the energy transfers. Now, one thing I need you to understand is, in order for an energy store in order for energy to go from one store to the other, it has to use an energy transfer or an energy pathway. And this is... Thank you, Max. Don't worry, Motives. It's the classroom I teach Max in. Right. So... how do I remember the energy stores easy? Honestly, Motives, I wish I could tell you there was a way. I've just done it so many times now. I will upload this, Angel, don't worry. I've done this so many times now that there's just no... I just remember them. And that is literally... one thing I do is... one thing I do for my students is I get them to do a quizzes in class. If you go to quizzes, QUIZZ.com, you can look up energy stores quizzes and you just do them again and again until you understand it. Honestly, no worries, it's all good, Motives. I appreciate you. Right, chemical, elastic, gravitational potential, nuclear, mechanical, kinetic, magnetic, thermal, and electrostatic. Now, if I had, and the easiest one I can think of is a slingshot. If I had a slingshot, I would obviously I would have to stretch the kinetic energy, so it's going to be chemical energy, and that transfers to kinetic energy inside my body. How does that happen? That happens through heating, and then as that energy is released, that kinetic energy is used to increase the elastic potential energy. And how does that happen? Well, it's through a force, my hand on the slingshot, so that's going to be mechanical, and then that stored elastic potential energy until it's released as kinetic energy again when I let go of the slingshot, and again that is mechanical. So when we talk about mechanical, we are talking about forces, okay? When we are talking about mechanical, we are talking about forces, and that's one thing that you need to understand in case they ask you to talk about an energy transfer, okay? Now, going back to this then, which energy store increases between position A and B? Well, I've got gravitational potential energy here. What type of energy has he got just before he lands? Someone tell me. What type of energy has he got just before they land? Tell me in the chat quickly. Tell me in the chat quickly. Good, well done, Isabella. They will have kinetic energy. Kinetic energy. Now, the child and the trampoline can be modeled as a closed system. What does the term closed system mean? Closed system is one in which energy cannot be exchanged with the surroundings. Hyper Des Moines, it's not gases, it's energy. It's energy, okay? You have to say energy. Exchanged with the one in which energy cannot be exchanged with the surroundings. And then, boys and girls, which of the following is the correct equation for calculating gravitational potential energy of the child? Luke, could you say released? Energy cannot be released to the surroundings. Yes, I'll give you that. Good, well done. It's MGH, it's the first one. Right, and then the next one. Next question. This is the last question then, boys and girls. So, A child has a mass of 30 kilograms. Now, with physics, you're going to get, especially on a higher paper, you're going to get to a point where you have really long mathematical equations. This one isn't too bad, but you will have ones that are slightly longer. Easiest thing I can suggest is underline your numbers as you go through. 6 meters above the ground at point A and 2 meters above the ground at point B. Gravitational field strength is 9.8 newtons per kilogram. Calculate the change in gravitational potential energy between points A and B, given your answer to two significant figures. Okay, so its energy is equal to mass times G times change in height. So therefore it's going to be a very simple. Mass is 30. I write it directly beneath it. G is 9.8 and height, or the change in height, is 6 minus 2, which is going to be 4 meters. So therefore I'm going to get an answer of 1176 joules. Now I can write that onto the answer line, but I would lose a mark, because what's the key thing they've asked us to do in this question? What have they asked us to do in this question? Someone tell me? 2 sig. Good, well done. Good, 2SF. So it's going to be, which is approximately equal to 1200 joules. So my final answer is going to be 1200 joules. Right, boys and girls, are we happy with that?